Okay, we are live. This is D. Thomas, Professor T, doing statistics. We're going to be doing the practice uh, statistics final exam. This covers chapters 6 through 10, and it's just a bunch of random problems. I haven't seen these problems, haven't really worked them out before, so I'm just going to give it a shot and see how it goes. Hopefully I can get 100%. Um, Although I've always said 99 is just like 100. So if I can if I can get above 98, um, I think that would be good. But definitely I'm going for a solid 100, guys. I have to do it. I have to get 100. If I don't get 100, I'm going to be mad. So let's take a look at the practice and see how it goes. I do have my calculator ready, and I'm using OneNote to take notes. And I know that the problems are going to be random. We get an awful lot of time, but for 35 questions, I think I should be able to do it in about 45 to 50 minutes. I don't expect to take that long. Um, but I think the projected time was about 120 minutes. This is a lot of problems. The actual final has, I believe, 25 questions, so it's not going to be as long. Anyway, let's give it a shot, and I'll see um, how this goes. I think the important part is just trying to identify the kind of problem you're dealing with. I think once you're able to identify the kind of problem, you're off and running. All right, so it says a data set includes 110 body temperatures of healthy adult humans for which the mean is 98.1 and the sample standard deviation is 0.64. Completes parts A and B below. They've given us a t-distribution. Maybe that's a huge hint. Maybe maybe that's a hint telling us that we need to do the t-distribution. Well, the truth is we would have to do the t-distribution if we're not given the population deviation. So the first thing it says is, what is the best point estimate of the mean body temperature of all healthy adults? And when they say all, they're talking about the entire population. Based on our sample of 110, what would be our best point estimate for every healthy human being? And that is the mean of our sample. And so I'm just going to put in the mean of the sample in there. And now I'm going to move on to the next part. It says B, using the sample statistic, construct a 99% confidence interval estimate of the mean body temperature of all healthy humans. Do the confidence interval limits contain 98.6? What does the sample suggest about the use of 98.6 as the mean body temperature? Okay. And then it says here, they want us to put the confidence interval in this form. All right. So basically, I need to construct a confidence interval, and the confidence level is 99%. So I'm gonna take out my calculator there, and I'm gonna go to confidence intervals for the mean. So we're gonna go over to tests and go over all the way down to t-interval. The t-interval should work for me. I'm given the sample stats, I'm given the mean, and I'm given the deviation, and I'm also given the sample size. So I'm going to plug all those values in. The mean was 98.1. Clear that out. The deviation was 0.64. And I'm forgetting the sample size, 110. And this is really important. They gave us the confidence level. They should always give you the confidence level. And the confidence level is 99%. So that's just going to be 0.99. It took a while to think it through. It took a while. And this is it, the T interval. I used the T interval instead of the Z interval because the reason why I used the T interval was because I didn't have the population deviation. All right. So let's see if this works. And they want us to run it to 3 places, but I don't even have 3 places. Oh no, I'm a little worried that I'm going to be entering in data that's not even, that it's not estimated properly. Hopefully there I can still get it right. So we got 97. Let's see, what was my interval again? I think I just lost it. We go back in there, stat, tests, and we said the T interval, number 8. And in the end, we get 97.94. And 98.26. Does the confidence interval contain the limit of 98.6? And I'm going to say no, it didn't. And then it also says, what does this suggest about the use of 98.6 as the mean body temperature? And what I'll say is this suggests that the mean body temperature could be lower than 98.6. This suggests that the mean body temperature could very possibly be 98.6, or this suggests that the mean body temperature could be higher than 98.6. So my interval basically suggests that it could be lower than 98.6. Now, we do have a very high confidence level, which means the interval is very small. Actually, very wide considering we're like almost certain that the true population is in here. So this is considered to be a wide interval. All right, I guess that's it. Now I'll just go over. Next, it says assume that adults have IQ scores that are normally distributed with a mean of 100 and a standard deviation of 15. Find P15, which is the IQ score separating the bottom 15 from the top 85. Alright, so again, what does this look like graphically? And I really need to center this. This is uncentered. If we have 100 in the middle, and so on and so forth, they want me to calculate the 15th percentile what is this value that separates the 15th percentile from the top 85 percentile? Let me make sure I got that right. Bottom 15%, top 85, so P15, that's what P15 represents. And so I know just what to do. I'm going to use inverse norm for this. So I'm just going to go to stat clear, go over to, actually stat doesn't help me. I need to go to second distribute and then find inverse norm. And it's probably best to put in, well, it's just going to be 0.15, comma 100, comma 15, which is the standard deviation. So inverse norm can take in 3 values: the area to the left, the mean, and the deviation. But the truth is I actually want to put on stat wizard. So I'm going to go to mode, and put back on Stat Wizard to make sure that I've got my order right. And now when I go back to second, distribute, and number 3, they're going to prompt me. The area to the left is 15. The mean is 100. Deviation 15. And then I'm just going to paste in my answer there. Let's see. Okay. So it does, inverse norm accepts 3 values. The area to the left, the mean, and the deviation. I'm getting 84.45 in both cases. Well, I need to make sure I rounded it properly. I'm not even sure. 84.45, that is rounded good. Alright. And they said to the nearest hundredth. Okay, good. Alright, now this is a 10-3 question. We're going to be using the regression line to make predictions. So let's just look at this. It says, suppose IQ scores were obtained from randomly selected twins for 20 such pairs of people. The linear correlation coefficient is 0.887. And the equation of the regression line is negative 3.24 plus 1.04x, where x represents the IQ score of the twin born first. Also, the 20x value have a mean of 93.626, and the 20 y values have a mean of 93.55. What is the best predicted IQ of the twin born second, given that the twin born first has an IQ of 97? Use a significance level of 0.05. Well, first I need to know if my correlation coefficient of 0.887 is significant or not. If it's less than the critical value, or actually if it's more than the critical value, then my regression equation is good. So I need to look this up. I need, for a sample size of 20, and my alpha is 0.05, so I'm looking for the critical value. What does the R need to be in order for there to be a regression line? In other words, what does the R need to be greater than in order to make sure that this is actually a strong correlation? Alright, so I need to go over to 20, and it just needs to be above 0.44. My coefficient is way above 44. It's 0.887. So that means we definitely have a positive correlation, and this is my best estimate. Now, the only other thing you needed to know is if the correlation coefficient was not greater than the critical value, then you cannot use this equation to predict. And the best prediction would be the average of all the y values. I'm not going to use the average of all the y values for my prediction because I know that this regression line is the best predicted value. So what I'm going to do is plug 97 into the x and solve for the y. So 97, I need to do, let's get back to the home screen. I'm going to do 97 times 1.04, and then I'm going to subtract 3.24 from it. And what did we get? 97.64. Yeah, I guess that's what we got. Let's move on. Alright, here's another problem. This looks like it's coming from section either 8.2 or 8.3, I want to say. Um, it's always good to kind of identify the kind of problem you're working with. So it says in a randomized controlled trial, insecticide treated bug nets were tested as a way to reduce malaria. Among 302 infants using bed nets, 20 developed malaria. Among 261 infants not using bed nets, 30 developed malaria. Use a zero point zero 0.05 significance level to test the claim that incidence of malaria is lower for infants using bed nets. Do bed nets appear to be effective? All right. Interesting. Interesting. So we we are gonna carry out this test here, and it looks like we're given a bunch of information already. Let's see, test for difference here. We're getting this. We're also getting the p-value. So they're giving us a lot of information. But what we have to do first is identify our null and our alternative first. So that's what I'm going to do. I already know that the first one will be equal to, and the next one will be either greater than or less than. It all depends on which is our first population. So let me go back and read our first. What would be our first population? It says insecticide treated bud nets were tested as a way to reduce malaria. Among the 302 infants using bed nets, 20 developed malaria. And then among 260 not using it, 30 did. And then it says test the claim that the incidence of malaria is lower for infants using it. Okay. So the first population is using it. And so what we're going to do is set up our null and our hypothesis like this. The assumption is that, first of all, there is no difference. And then the claim, we're going to see if we have enough evidence to support the claim that the first population, the people using bud nets for the entire population, is better. If it's true, then guess what? Then it's a fact. It's like a proven fact, kind of. A statistically proven fact that the entire population, that everyone should use the bed nets. And all bed nets are just a net that you have to sleep inside of, and I guess it's a really small opening for them to get through. Identify the test statistic. So it looks like the test statistic is given to us as negative 2.03. That's our z-value. And identify the p-value. Well, the p-value is 0.021. This is a single tail test. It looks to be a left tail test, actually. And now what is the conclusion? Well, the p-value is less than alpha of 0.05. So the p-value is less than the significance level alpha. So we reject the null hypothesis. And remember, the null hypothesis said that there is no difference. We have to reject that based on our evidence. And now we can say that there is sufficient evidence to support the claim that incidence of malaria is lower for infants using bed nets. The bed nets appear to be effective. That should complete the test there. I don't like how they don't tell you whether or not you're right or not. You actually have to you have to do the whole thing. So yeah, we have to actually do the entire thing. So it's going to be pretty interesting. And I guess also reviewing. The practice is set up in a way to where if you review it, well, I've already took 20 minutes. I've done 5 problems. I gotta pick the pace up. uh, Reviewing is always great. You learn the most right after the test. So after you do this, you could print out the solutions and everything. So let's get shaken on this. It says assume that the readings of thermometers are normally distributed with the mean of 0 and a standard deviation 1. That's the standard normal distribution. Assume 3.1% of the thermometers are rejected because they have readings that are too high, and another 3.1% are rejected because they have readings that are too low. Draw a sketch and find the two readings that are cutoff values. Okay, so there's going to be my sketch. And the cutoff reasons is because this is symmetrical, I simply need to find the inverse norm of one of them and we'll be good to go. So I'm going to find the negative one. I'm going to be really lazy and just do the inverse norm of 0.031, and I believe that's 3.1% to the left. I need to make this 0 again, and I also need to make this 1. And let's paste this. It should be negative. So negative 1.87 if I round it off. And then also positive 1.87 because it is symmetrical. Here's another problem. This time we're dealing with the sample mean of two sample means there. A study was done on body temperature of men and women. The results are shown. Assume the two samples are independent SRSs selected from normal distribution populations and do not assume that the population standard deviations are equal. So we have to use a t-test here. And so this is what we'll do. Actually, not that. Let's try that again. I clicked on the wrong thing. So this is what I'm going to do. I'm going to enter the value, the information in as a test. So the first thing we have to do is find the right test to use. We're dealing with means because that's mu, that's the population mean. And so we have a sample of each population. And so what we'll do is go into stat, go over to tests, and we're going to be looking for the two sample t-tests. That's exactly what we need, the two sample t-test, not the z-test. The z-test is used when we have the population deviation. We don't have it in our case, so just hit enter. We're given the stats of each one, so I'm going to enter in the stats of each one. I have the mean of the first one is 97.7. $97.77. Standard deviation of 0.79. And the sample size is 11. The next thing I got to do is put in the second sample. So the mean of the second sample is 97.34. And my standard deviation is 0.65. And the sample size there is 59. Now, I do have to be careful of what is my alternative. I need to make sure that my alternative is set up properly. So I need to read the problem. It says test the claim that men have a higher body temperature than women. Okay, so men is the first population, women the second population, and so we're going to test the claim that mu1 is greater. Now we don't have the population, so we're going to use a sample. And this test is so powerful that the results imply the population. So we're definitely going to go with this one, and that means now I know how to set my population mean up. Mu1, we're assuming that mu1, our claim is that mu1 is bigger the mu2. It is not pooled, and we just calculate now. Let's make sure that we entered the values in good. Okay, that all looks good. And I got a test statistic, and my p-value is 0.05. So my test statistic, if I round it to 2 places, I got 1.70. My p-value was 0.057 when rounded off. And now the p-value is not less than our alpha, which is in our case 0.01. It's not less than it. So the p-value is not less than alpha. So what does that mean? Well, we cannot reject the null. The null that they're equal, the equal means could be correct. We don't know. We can't reject it. The claim, we did not prove the claim statistically. So we'll fail to reject the null. There is not. So we'll say fail to reject the null. There is not sufficient evidence to support the claim that men have higher mean body temperatures than women. And the next thing we're going to have to do is create a confidence interval to kind of support this as well. And we'll probably create a confidence interval, and 0 may be in the interval, which also implies that it's possible that the difference between the two population means could be equal. Their difference is 0. So let's create a confidence interval. But okay, the thing is they didn't give us the. They actually didn't give us the confidence level of our confidence interval, and they should have. But because we're using a significance level of 0.01, so 1 tell is 0.01, we'll use a 98%. And the reason why I'll use 98%, let me demonstrate this. I want it to be consistent. So this is dealing with the bottom 1%. This is our critical value, our alpha. Now, when we construct a confidence interval is done in both tells. So if we want a confidence interval on 1%, the other side must also be 1%. And what does this mean? It means that the inner level is 98%. Because we're dealing with 1%. We want the 1% to match. So I have to set my confidence level of 98%. And that's what I'm going to use for mine. Now, the cool thing about this is I think it's already going to be set up for us. So we just go into Stat, Tests, and then instead of 2-sample t-tests, we're going to go to a 2-sample t-interval. The stats are already set up for us, but they're using a 0.99 confidence level. I'm not convinced that that's going to work. I'm going to use a 98. Let's see. All right. So this is what I got, and it turns out that 0 is actually in the middle. So let's put these values in. Round to 3 decimal places. That's not going to be a problem. We'll do negative 0.243, and then also 1.103. And we'll say, does the confidence interval support the conclusion of the test? Yes, it does, because the confidence interval contains 0. All right. let's see, I may only do half this test. Let's keep going. It says the weights of certain brands of cereals are normally distributed with a mean of 0.8591 and a standard deviation of 0.05. A sample of these candies came from a package containing 447 candies, and the package label stated that the net weight of 381 g grams. Packet has 447 candies. The mean weight of the candies must exceed 0.8535. So, okay, let's answer this. So the first step is, if one candy is randomly selected, find the probability that the weight's more than 0.8535. All right. So what we'll do, this comes from chapter 6. What we'll do is go into second, distribute, and we're going to be using normal CDF here. And our lower bound is going to be, because we want to know the probability that weights are from 0.85 on up. So my lower bound is going to be 0.8535, and my upper bound is going to be all the way maxed out. So a very large number. The mean of the candies is 0.8591. The standard deviation is 0.0571. So the probability of selecting one candy that will weigh more than 0.8535 is more than 50%. It's actually going to be 0.5391. And now part B. The probability, what would be the probability that a sample of 447 candies will have a mean of 0.8535 given the same conditions? So what we'll do is, because everything else is the same, I'm gonna do a second entry, and that standard deviation, it's going to be the square root of the sample size divided by the square root of the sample size. Now, what was that sample size again? 447. And we're getting 0.9809. And now we're going to answer the question, given these results, does it seem that the candy company is providing consumers with the amount claimed on the label? I would say yes, because the probability of getting a sample mean of 0.8535 or greater with 447 candies are selected is exceptionally, hold on. So we're going to say that yes, because the probability of getting a sample mean of this value or greater when 447 candies are selected is not exceptionally small. It's really large. The chances of this happening is 98%. Okay, so we have this problem here, and what we're going to do is put in L1 and put in L2, and yeah, that's what we'll do. So we're just going to manually enter these into our lists. Court income will be list 1, justice salary will be list 2. That's the first thing I'm going to do. So I'm just going to take a moment and enter these values into a list. In fact, I'll use list 3 and list 4. $405, 1566. Just going through the steps. Let's see. This is actually taking a pretty long time. $112, 156, 32. So we got 9 values in there. Let me check. 1, 2, 3, 4, 5, 6, 7, 8, 9. And now the second list, I need to put in 30, 42, 91. Let's see, 30, 42, 91. $56. Yeah, we may cut down our test. We may only put 20 questions in there. This is taking too long. 25. That's a lot. All right. So I put the values in list 3 and list 4, and now I'm going to carry out the test. Well, before I carry out the test, I do need to make sure that our null and alternative is correct. So it says listed below are amounts of court income and salaries paid to the town justices. All amounts are thousands. Construct a scatter plot. Find the value of the linear correlation coefficient R and find the p-value using alpha 0.05. Is there sufficient evidence to conclude that there is a linear correlation between court income and justices? Okay, so this is just your simple row is either 0 or it's not, which is the population correlation of all court incomes and all justices. And the scatter plot, I can actually use my technology to create a scatter plot really fast. What I'll do, and maybe that will help me graph it. I'm going to do second stat plot, turn the first plot on, and then I'm going to choose L3 and L4. And then just go to stat plot. So zoom and then number 9. So this is what I got. That looks familiar. I think it looks like B. And then next, the linear correlation coefficient R is what? Well, I need to actually figure it out. I go to stat, tests, and go all the way down. It's pretty far down. The linear regression t-test, F. We're going to do L3 and L4. And we're saying that rho is not equal to. And I can put my regression line in there. I might as well. Which stores my regression function. It will store my regression function into Y1. And now just hit calculate. So I'm getting, oh wow, look at how small that p-value is. My test statistic is pretty large, 4.49 or 4.50 if we're rounded. The the correlation coefficient. What did we get for that? Let's see. In fact, let's split the screen so we can see both things. Okay, so I have to go down further to get the R. So the R is 0.862. And the next thing, the test statistic, 4.497. And then finally, the p-value, we're getting 0.003. The p-value is going to be less than alpha. So because the p-value is less than the significance level, there is sufficient evidence to support the claim that there is a linear correlation between the court and the income. So based on the results, does it appear that justices might profit by levying larger fines? Well, yeah, the larger the fine, because there's a correlation, absolutely. Now, but this I'm also starting to think that maybe we could have set up our well, we could have also done B as well. So it's actually to make our alternative not equal to that, that means that there's a negative correlation, and we're not seeing a negative correlation. All right, we believe it is a positive correlation. So B is just as good. B is just as good. You shouldn't be wrong there. But anyway, yes, it's true. A larger fine, because there's this correlation between the income of courts and justice salaries, we could say that. So based on the results, does it appear that justices might profit? It does appear that justices might profit by issuing smaller fines. It does appear that justices might profit by levying larger fines. It appears that justices profit the same. So I'll choose D. The area of the shaded region, we're talking mean, 15. That's normal CDF all day. Normal CDF. So we're going to do second, distribute. Number 2, my lower bound is 80. Upper bound is 115. And my mean was 100. And my standard deviation was 15, I believe. Let me double check that. Yeah, it was 15. .7501. Alright, so here we're going to create a confidence interval, but we have to put this into a list. So I'm just going to put this all into list 1. Let me clear my lists out. And now I'm going to put those values into my list. So we're getting let's see here, 4,048, 3880, 3880, 3862, 4037. This is really good practice. 4317, 4810, 4667, 4029. I'm really slow at this part. 5011. 4831. And we have 4344. Let's see. And 4309. All right. So there's everything in my list. Now all I have to do is create a confidence interval, but I need to know what kind. Well, I'm given the mean and the sample, and my confidence level is 90%. So that's all I got. Let's get out of here. Oh, 40. Okay. So now we go into stat, tests, and it's just going to be a t interval. We're given the data is L1, and my confidence level is 90%. For 4139.6, 4551.3. Round to 1 decimal place. Yeah, no problem. That's it. That's pretty much it. Yeah, I think I'm gonna do about, I'm gonna go up to 15. I want to see how I do, so I'm gonna probably just end my test. I'll probably do another test. It's not good to have very long videos, so I'm gonna do a few more, and then let's see what let's see how we do. So anyway, it says to construct a confidence interval using a given confidence level, do whichever of the following is appropriate. Find the critical value z alpha 2 or b. Find the critical value t alpha 2 or c. State that neither the normal nor t-distribution applies. We have 99% confidence level, and our n is extremely large. N is 400. Sigma is unknown. Population is skewed. That doesn't matter too much. But because sigma is unknown, we do have to do a t alpha over 2. And 99%, which means alpha is 1%. So what we could do is get the value this way. Since alpha is 1%, half of alpha is 0.05. Yep, right here. Degrees of freedom, 400. I don't think it goes up that much. Oh wait, we do have 400. Wait, what column is 0.05? The second to last column at 400. 1.649 is good. 1.649. That's what I got. Wait a minute. Let me double check that. It's more like, well, this is 5%. So 1%. Okay, so half of 1% is 0.005. Okay, I was mistaken. So we're doing 0.005. Very, very tiny. It's way out there. 400 of the first one, that's 2.58. There we go. That's more like it. Now, how could I have done this in my calculator? We could have done it in the calculator. If you have inverse t, you just simply do, it'll be negative. I'll do second distribute and then inverse t. and the area is going to be 0.005. Degrees of freedom 400. That's it. Area to the left. It'll be negative, but we'll make it positive. Negative 2.588. So assume a significance level of alpha 0.05 and use the given information. Original claim is that the proportion of male golfers is less than 0.2. So the hypothesis test results in a p-value of 0.03. State a conclusion about the null hypothesis. Well, because the alpha is 0.05, but our p-value is less than that. So this is great. We get to reject the null because the p-value is less. And now, without technical terms, state a conclusion. Well, there is sufficient evidence to reject the claim. No, we're not going to reject that claim. That claim, we're supporting the claim. So we'll say is, there is sufficient evidence to support the claim. Yeah. Alright, that one was kind of fun. Alright, let's do a couple more and then we'll probably just wrap it up. Trials in an experiment with a polygraph include 97 results that include 27 cases of wrong results and 73 cases of correct results. Use a 0.05 significance level to test the claim that such polygraph results are correct less than 80% of the time. Identify the null and the alternative. And so on and so forth. So we have two. So well, we're dealing with what they're saying is that let's say use a 5% significance level to test the claim that such polygraph results are correct less than 80% of the time. All right, so that's more like we're dealing with this guy. H null is 80%, the alternative is less than 80%. So our claim is that that it's correct less than 80%. And our success, out of 97 results, 73 were correct. There's a proportion for us right there. So let's use our calculator now. Let's do this problem. It's interesting. We go to stat, tests, and we're going to do one prop z test. And we're doing, our null is what did we say? 0.80. And we're talking success. Now our sample was 73 out of 97. And then we're gonna say that the alternative is that it's less than 80% correct. And now just hit. So our estimate was 75%. Based on that sample, we had 75%. Our test statistic is -1.6, and our p-value is 0.12. So let's enter all these values in. Our p-value is not that small. So let's do this. It says the test statistic is z equals -1.17. I'll round it off. The p-value to 4 places is going to be 0.11215. And then we need to state a conclusion. Well, we're going to compare our p-value with alpha of 0.05. So Identify the conclusion about the null and the final conclusion that addressed the original claim. So what we'll do is say we're going to fail to reject the null. There is not sufficient evidence to support the claim that polygraph results are correct less than 80% of the time. We cannot state that. It's because the p-value was not less than alpha. So that's what we got. We're sticking with it. We're gonna do up to 15. I can't believe it's taking me this long. Find the indicated IQ score, and let's do this. It says the graph to the right depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. So we have mean 100, standard deviation 15. We have the area to the right, but we want to know the x value that separates the top 85 from the bottom 15. So I can use inverse norm here, but I can't put in 0.85. I need to put in the area to the left. The area to the left is going to be 0.15. So this is what I'll do. I'm going to go to second, distribute, and do inverse norm. And we're going to put in 0.15. And we're dealing with 115. And this should give me the score 84.5. That's the score. 84.5. And let's do this one. All right, we're going to wrap it up after this one. Let's do this one. All right, here we go. In the week before and the week after a holiday, there were 10,000 total deaths, and 4,948 of them occurred in the week before the holiday. Construct a 95% confidence interval to estimate of the proportion of deaths in the week before the holiday and the total deaths in the week before and after. Based on the result, does there appear to be an indication that people can temporarily postpone their death to survive the holiday? Well, first let's do this. We're going to construct a 95% confidence interval, and all we're given is that out of 10,000 deaths, 4,948 of them occurred in the week before the holiday. So that's almost half. The percentile of deaths. Let's use this. So where are we going to go for this? Well, this is actually going to be a one prop z-test, or one prop z-interval. So let's find that. I think we got to go pretty far down. One prop z-interval, that's A. And we're using 4,948 out of 10,000. And our confidence level was 95%. And now all we're going to do, we're going to wrap it up here. We're going to split the stream into another part. There's just so much more we need to do, and we just don't really have the time. Oh, and there's actually been some questions. I haven't seen these. Oh, I got it. Did you already finished in 3? No. All right. So let's hit calculate in our confidence interval. Okay, look at that. We have a confidence interval, the percentile of deaths based on the sample. It turns out to be 0.485 and 0.5056. Well, 50% chance is inside this interval. In fact, this interval goes up to 50%, which basically means it does not really matter. So let's put this in. 0.485, and then our other interval is going to be 0.505. And it says no because the proportion could easily equal 0.5. Absolutely. All right. That's what I got. That's what I got. So I'm going to submit my test. We've done 15 problems. There's an awful lot of problems left. There's like 20 something questions left. But let's see how we did. And what we'll do is see. Wow. Let's see. You have not completed your seminar. Are you sure you want to submit? Yes, I'm sure. I'm sure. Well, the test was pretty good, but let's see. There's something going on in question 4. Oh, so we chose the wrong. We chose the wrong population to be P1. I thought the first population was the infants using bed nets. Everything else was okay. How could this be right? Especially if our test statistic is negative. Get out of here. This isn't. Wait a minute. Oh, yeah. Absolutely. Yeah, okay. So we did switch that around. I guess that was legit. We're dealing with one tell and our test statistic was negative. It should definitely have been, the first one should have been, the first population should have been greater. I don't know what I was thinking there. It's really odd. And the other question, let's see. There were 2 questions that, and I got 0.86 on, and the other one half a credit on. Everything else worked out. But we were doing pretty well. We were doing pretty well. We just couldn't finish. This thing was too long. Way too long. If one candy is randomly selected, find the probability that it weighs more than 0.8535. I answered 0.5391. .98. Did I mess this up? Oh, wait. Wait a minute. Let's go back to this problem. I kind of remember this problem. It was 0.85. Oh, the mean was. Are you kidding me? We put in. We were supposed to put in the mean of point. Oh, no. This is good. This is good. This looks good. What about my standard deviation? Yeah, my lower bound is 0.8535. My mean is, so lower bound to infinity, and then my mean is 0.8591. That looks good. And then my deviation was 0.0571. Yeah. 0.53. Oh, I didn't put in the right value. I got 0.539. What did I put in? I put in 5.4? Why would I do that? Yeah, I did. I did get that one. That was really weird. And then the other value is this value times the square root of 4. Divided by the square root of 447. Point 0.98. Oh, 0.9809. No, my answers are correct. This should not be wrong. This should not be wrong at all. In fact, my answers are more precise than theirs. I think they've used a table, but our answers are very precise. Yeah, so we actually have the mean weight at 0.85. It's really a puzzle um, how my answers could be so close, but they're still off. Um, this just doesn't. Their values just don't seem right to me for those two values there. Especially seeing how close this one was too. It was really weird. 0.85. The weights of a certain brand of candies are normally distributed with a mean weight of 0.8591 and a standard deviation. Yeah, I don't know. Something about that one just seems really odd. So what you'll do after you've completed the test, um, yeah. So for number four, that was just a fluke. It 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 was misinterpreted which one. They should have told us which one was the first population because I chose that the first one using bed nets was my first population. And then we wanted to state that using bed nets will help you. And so we were supposed to choose F, and I think I mistakenly. So this was just an error on my part. But we did understand this one. Using bed nets is here, population one, and not using bed nets is there. So that was pretty rough. Um, And it appears that this one might be wrong, um, but I just need to check this. Point 8535. So we're doing lower bound, upper bound, lower bound, upper bound, mean. And then standard deviation. Point 5391. Yeah, I think they got their values using the table, um, and we did ours using more of a precise measurement. So, all right, guys, we're gonna wrap it up here. I think I'm gonna cut down this test. This is really intense. This is a lot of problems. I just did 15 problems, and it took me quite a long time. So, um, I can kind of sympathize. We might do some more problems some other time. But just to kind of help. Hopefully, this was helpful, and we'll come back um, with more videos soon.